Today I'll be going through some comments on linear algebra in the context of further math. So I'll be namely going through some of these ideas, numbered 1 to 4 over here, and in so doing I'll be solving this question, which is showing that the dimension of a column space and the dimension of a row space are equal, and we know that's equal to the rank. So so without further ado, let's jump right into it. So let A be a m by n matrix representing a linear transformation from Rn to Rm. So what this means is that, for example, if A is let's say A is a 3 by 2 matrix. So example, if A is a 3 by 2 matrix, and we have A equals to, let's jump over to Wikipedia here for the example. So if we have A equals to 1, 0, 0, 1, 2, 0, then you can see that A, it maps R2. So this is N and this is M. So it maps R2. So let's say it maps 2, 1, and it maps it to 2, 1, 4. So you can see that A is, it maps a 2D vector to a 3D vector. So this is what I mean by A represents a linear transformation. So actually what we mean by really representing is that we are making a choice of bases for both the domain and the range, but I will not be going to that. So so actually that is in fact point 1. So the first point we can talk about is that what's the difference between a matrix, which is a matrix is a table of numbers, okay, a table of, let's say, real numbers in our case. And what is the difference between a matrix and a linear map? So a linear map is defined by its linear properties. Let's say a linear map T from a vector space V to another vector space W. Then the linear map is defined by properties of linearity, namely T A plus B equal to TA plus TB. So and also scaling. So T lambda of A equals to lambda T of A. So what is the difference? Actually, what the key idea is that we start off with a linear map, right? And when we have a vector space, so right now imagine an abstract vector space. So the vector space can be thought of as arrows in some abstract space. For example, it's a 3-dimensional space, right? So once the more you know that it's 3-dimensional, you can actually choose a set of bases x, y, and z. And let's say we have the vector v, then this can be written as linear combinations of basis vectors. Okay, it's probably better to write I, j, and k. So I, j, and k. So then when you have a vector, you can write it as a linear combination of the basis vectors. So you have xi plus yj plus zk, right? And then these can be represented as a column vector x, y, and z. So that is what is the difference. So in order to first understand the difference between matrix and linear map, we first discuss the difference between a vector V versus a column vector. So a column vector is a n by 1 matrix, in a sense. It's a vertical list of numbers, and a vector is an element of a vector space. So the difference here is that so when you have a vector, right, it lives in some abstract space, and you make a choice of a basis, namely you choose one such example is I, j, k, but there can be other choices of basis as well. So this is valid basis 1. There can be other valid bases as well. For example, I plus j, I minus j, and let's say 2k. then you see this is another valid set of basis vectors 2. So when you after making a choice of basis, vectors, then you can obtain the components of the vector and we put it in a column vector, and that is how you go from a vector to a column vector. In a sense, you take the vector and you project it down to the basis vectors to obtain the column vector. And so actually that's the key difference between a vector and a column vector. And in a very similar spirit, the linear map represents an abstract transformation on this vector v. It acts on the vector space and gives you another element of a vector space, but a matrix is a representation of this linear map in two choices of bases, namely so to go from linear map to matrix, you make a choice of basis for number 1 v and number 2 w. So in essence, to go from a vector to a column vector, you need to make a choice of basis, and then to go from a linear map to a matrix, you need to make a choice of basis for the two vector spaces involved, the domain and the codomain. So this guy and this guy. Yes. So there's a difference between a matrix and a linear map. So now we'll be focusing, that's just an aside, we'll be focusing our discussion on the matrix representation purely. So number 2, the column space is the range. Okay, what does the range mean in the first place? Range means that we know that A is a matrix. Matrix A is a map from Rn to Rm, right? Now, by purely the fact that A takes in any vector, any column vector in Rn, it means that we imagine choosing every single possible column vector in Rn, meaning that if, let's say in the case where n equals to 2, then we are thinking of 0.1, 0, we're thinking of 0.01, 0, we're thinking of all the possible 2 real numbers they can write down. So that is all the possible, we're thinking of all the possible 2 real numbers, and then we form each one of those combinations into a column vector. So for example, 1, 0 would be inside Rn, same as pi e would be also inside Rn, where n is 2. Okay, so we think of all the possible 2 real numbers and we put it in a column vector format, and then we apply this matrix A on them, and that will give us something over here. So that will give us some three component vector, and this will also give us some 3 component vector. So what is the range? The range is after considering all the possible 2 real numbers on the left hand side, we collect whatever has been spit out on the right hand side and we collect it into a set, and this set will form a vector space. Actually, it will be a vector subspace of Rm. So that is what the range means. In other words, is the image. So you might hear it as the image as well. So if we represent it abstractly, we have Rn and then we have Rm over here. So the Rn would map to some huge proportion of Rm under this this matrix A, but it could possibly be not all of Rm, meaning there are vectors in Rm, for example this one, where there is no v in there's no 2D vector that that gives this vector. So if there's a w over here, then so there does not exist v in R2 such that AV equals to w. So yeah, so if in fact all the vectors are covered, then we call this map an onto map. But if but in most general case, especially in the case where n is smaller than m, then this Rm would not be covered completely. So this space is what we call the image of this linear transformation. So what does it mean by column space is the range? So in order to see that, let's go into some numbers. So we have 1 0 0 1 2 0, let's say. Okay, so now we represent any vector in R2 with x and y. So x and y live in R2, and we have not placed any conditions on x and y, which are real numbers. So this, in a sense, this x and y represents every single possible vector in R2. And what do we get? We get, if we multiply this out, this is AV, we get x times 102 plus y times 010. I could have written this out in addition form, meaning x, y, and then 2x, but I'll stick to this because I want you to see that essentially this is a span. So essentially this is a span of the vectors 102 and 010. You see that because x and y can take on any possible real numbers, any real value, then essentially the range of A is equal to the span of these two vectors. And what's the span of these two vectors? We call it the column space. Why do we call it the column space? Because they are the column vectors in this matrix. So it is a very simple idea that we take any possible vector in R2, x and y, and then we let A act on it. And what is the range of this linear transformation A? It is simply the span of these two vectors. Because why is it a span? Because we allow any arbitrary values x and y, and that is what the span means, any linear combination of these two vectors. And that is what we call the column space. So the column space, if we go over to Wikipedia, the column space is also called the range or image of a matrix, which we have just talked about, is the span of its column vectors. The column space of a matrix is the image or range of the corresponding matrix transformation. Yes. So yeah. And so that is what the column space is. And I hope that is very clear. So now let's talk about the row space. What is the row space? The row space, similarly, if we have a matrix 1 0 0 1 2 0, then the row space is going to be the span of all these row vectors. So row space of this equals to span of 1 0 0 1 and 2 0. So it's a span of all these three vectors, and we know that we can eliminate one of them, but it's essentially the row space is by definition the span. The row space is the span of all the row vectors. So it's a linear combination, which is what a span is, of these vectors of this form. So in other words, it is all the A plus b plus c for all a, b, c in real numbers. Okay, so what is the row space? Previously we saw that the column space is the range, right? But what is the row space? The thing is actually the orthogonal. The row space is the orthogonal complement of the kernel of A. So first of all, what is the kernel of A? The kernel of A is defined to be all the vectors in the domain, which is Rn, such that A of V equals to the 0 vector. What this means is that, let's say, so in our example, let me think of an example. Okay, so in our example, the only vector that is mapped to 0 is actually the 0 vector, and that gives us 0, 0, 0. So if we think of it as Rn and Rm, there's possibly some set that is mapped to the 0 vector in Rm, and this kernel, we call this part the kernel, and the kernel lives in the domain. So okay, so the row space is the orthogonal complement of the kernel. So yes, so what does that mean? So let's say the kernel in this case is just the 0 vector. So the kernel, so the row space of A is the set of all vectors that are orthogonal to all vectors in the kernel. So let's say we have an example. Let's say we have a kernel which is let's say we have a kernel for another transformation B. Okay, we have a kernel that is a plane, some infinite two-dimensional plane. I draw a finite one here for illustration, but it's supposed to be infinite. It's supposed to stretch out to infinite. Yeah. Then what is the orthogonal complement of this? It is the perpendicular vector to this plane. Now that is because we live in this is the case where it's a three-dimensional space, but you can actually, in four-dimensional space, there are two directions that you can travel for the orthogonal complement, for example. So yeah, how do we see this? Let's go over to a new document. So actually I'll jump over the wiki now. So row space, relation to the null space. Null space is kernel. So the null space of a matrix is a set of all vectors that are mapped to 0, and because the product of the matrix, the linear transformation that we want, and any vector x can be written in terms of dot products of vectors. Later I'll show this. Thus, if x lives in the kernel, then x is orthogonal to every single row vector of A. And so x is orthogonal to the entire row space. So it follows that the null space of A is the orthogonal complement of the row space. So what this means is that because our matrix A can be written as rows, okay, where each one of the rows, row I equals to something 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 n. Then A acting on any vector v, if v lives in the domain, then it can be written as r1 dot product v, r2 dot product v, and so on, rm dot product v, where ri dot v is just the vector dot product. So we just have this thing n dot this thing with height n. So that just gives us a single real number. Because the dot product of two vectors is a real number. So what we see is that if AV equals to, if and only if AV is if AV is equal to all of the zeros, if AV is the zero vector, then all the rows when dotted with V equals to 0. So this is a real number, and this is for all index I from 1 all the way to m. And that means that any linear combination of the row vectors dotted with V is also equal to 0. And what do we see over here? This is just the entire span of Ri, which is equals to the row space. So the V, so if V lives in the kernel of A, then V is perpendicular to the perpendicular, meaning that the dot product gives 0, because when you have two vectors and they're perpendicular, the dot product gives 0, right? Yeah, and meaning V perpendicular to the entire row space of A. And that is what they mean by orthogonal complement. Yeah, so with that we are almost done. So in the end, showing the end result is not important, or rather showing the end result is important, but the key takeaway I want you to have from this video is the process of thinking of what is a row space and what is a column space. And so we're finally able to get on to the proving the result. So show that dimension of row space plus dimension, no, equals dimension of column space. Well, yeah, so we know first of all that the dimension of the kernel of A plus the dimension of the row space of A equals to n, where A is a map from Rn to Rm. Why? Because kernel of A is the orthogonal complement of row space of A. And when it's the orthogonal complement, these two dimensions better add up to the entire domain. So if you're not convinced, just imagine that I live in a 2D world, okay? So I live on a 2D world, and let's say my kernel is the horizontal okay, let's say my kernel is some line passing through the origin kernel of A. Then the orthogonal complement is going to be a perpendicular vector like that, a perpendicular vector space in a sense, orthogonal vector space. And it sort of takes up whatever remaining dimensions there are, because the dimensions sort of reflect how many perpendicular vectors you can have in the first place. So in the case where we have a 3D world, if we live in R3, let's say this is R2, then you see that the dimension of A equals to the dimension equals to 1, dimension of row space equals to 1, and you add up, you get 2. Whereas if you have a domain in R3 and let's say your kernel of A has dimension of 2, then the orthogonal complement would just be a line, and the row space and orthogonal complement of row space will have a dimension of 1, so they add up to 3. So with this, yeah, I hope that I've illustrated this fact clearly. Okay, and we also know that the dimension of column space is equal to dimension of the image of A, or in other words, dimension of the range, because we know the column space is the range. So with that, let's bring in the rank nullity theorem, which says that dimension of dimension of range, dimension of image plus dimension of kernel equals to n. And so we already see the very similar, so we see that the pink parts are the same, so dimension of row space is equal to dimension of the image, and we know that dimension of the row space, yes, dimension of row, so these are the same thing. Oh, here I meant to say column space. Okay, sorry, just now I meant to say column space. So this is actually the column space. Dimension of the kernel plus the dimension of the column space. No, this is the row. Oh yeah, correct. Sorry, I was correct all along. Yeah, so dimension of the row space is not the image. I'm so sorry. Yeah, so the dimension of the kernel here is the same thing. Then the dimension of n here is the same thing. So from that we conclude that the dimension of the row space is equal to the dimension of the image, and the dimension of image is equal to the dimension of the column space, and hence the dimension of the row space is equal to the dimension of the column space. And so in so doing, by using our geometrical understanding of what column space is and geometrical understanding of what row space is, as well as the rank nullity theorem, which makes no reference to matrices whenever it works in just the abstract sense of vector spaces, we have managed to prove that the dimension of the row space is equal to the dimension of the column space. And so with that, let's just make a short conclusion. So summary. Number one, we showed what matrix was versus a linear transformation. We saw that in the same sense is what a column vector is versus a vector in general. We make a choice of a basis to go into the numbers representation. Then we saw that the column space equals to range, because when you have these things, right, these are the columns of matrix, and you multiply by any real numbers, then you get x times this column plus the first column plus y times the second column plus z times the third column, and that is essentially exact. And if you let x, y, and z range through, let x, y, and z go through all the possible real numbers there are, then that is essentially what the span is, and the span of the column space is hence the range. Then we went through that row space is the orthogonal complement of kernel, and then we used rank nullity. And so what does this mean? It means that if a row space spans a particular vector space, let's say a plane, then the kernel is going to be a line that's perpendicular to the plane. Then we use the rank nullity theorem, and we showed that dimension of row space equals to dimension of column space. So that's quite a lengthy video today. I'm sorry that I speak really slowly, but I really need to make sure that I'm saying the right things. So yeah, I hope if you made it through the end, I hope that you have found this useful in some sense. And yeah, have a nice day. Bye.